All right, welcome back for the chain rule. Day number 2, as I promised, we're going to formalize it, and here we go. We're going to talk about Gottfried Wilhelm Leibniz from Germany, a great mathematical mind. Not only did he realize the chain rule and formalize it, but he also co-invented calculus along with Isaac Newton. No, they weren't friends and buddies. They didn't know each other. They weren't contemporaries. And in this guy's spare time, he also invented the binary system with all the zeros and ones. Basically, we owe everything that's digital to this guy that we enjoy in our present-day lives. But what he did with the chain rule is up here in the box. Our book calls it Theorem 2.10, but that's not its real name. It's called Leibniz notation. And here it is. dy dx equals dy du times du dx. So in other words, the way you read this formally is like so. If you want the derivative of y with respect to x, you need to take the derivative of y with respect to u, a y equals equation with u's in it, and multiply that by du dx, the derivative of u with respect to x, which is a u equals equation that happens to have the letter x in it. All right, we're going to explore that a little bit in the next few examples. But yes, Leibniz did invent calc, or he discovered calc, I should say, along with binary. So that's amazing. You know what else is amazing is that hair. Man, I was talking about that last year a little bit too with my classes. That's got to be a wig, man. That can't be real. I don't have hair like that. My gosh. He looks like he belongs in one of the 80s like hair bands. Like you could throw him right in the background with Whitesnake, give him a bass guitar, and just let him, go crazy. So, anyhow. All right, find dy dx, number 5. This is pretty intense. It's got trig in it. It's got 7th powers. Even the chain rule has exponents in there. So we're going to do it the way that we know already. And I'm going to turn around and do it with the Leibniz method so you can kind of compare and contrast. Sounds like I'm about to give you an essay to write. Not quite that crazy. All right, let's try this out. Again, I don't like the way this looks. So I'm going to rewrite it. There, much better. All right, as always, I'm going to start out with my first step being the power rule. Invisible 1 right there. Rather than writing y prime like I've been doing, I'm going to keep it formal with a solid dy dx in front. Okay, 7 times 1, of course, is 7. Stuff, which I'll copy in a moment, to the 6th. And the power rule step will be completed. Then we dig into the interior of the problem, inside the first set of grouping symbols, and we stare at that thing and say, hey, does sine of something have its own derivative? And the answer is yes, it does. It's cosine of stuff, cosine of argument. So you have to multiply by that. But then we go into the next level and we're like, does this next set of grouping symbols, the parentheses, have its own derivative? And yes, it does. All right, so we have to multiply by that. And that's going to be 3x squared plus 10x. All right, and then we just get ourselves a final answer. And I'll do that in black. Notice I moved the blue parentheses up near the front. You can distribute the 7 through if you want. You can get 21x squared plus 70x. You don't have to. If you do that, they both have to be inside parentheses, though, to preserve order of operations. You don't want to goof it up. I would just leave it like that. All right, that is the main way that we've been doing problems. It's the way that we're sort of familiar with. But I want to take the same exact problem, redo it using Leibniz notation. I'm going to leave the final answer where it is, though. All right, the first thing I'm going to do is I'm going to copy down the Leibniz formula. And it says dy dx is equal to, and this is how I memorize it, the dy needs to be on top because it's on top on the left. The dx needs to be on the bottom because it's on the bottom on the left. And then we have this third wheel in the problem. It's a du, and it's sort of like an imposter. And it sort of fills in the other slots. You can almost see the du canceling itself out, even though that's not completely mathematical. Let me get rid of those cancelings before somebody important walks in the room. All right, so that's the Leibniz equation. All right, for those people like myself in high school that I would go too far or not far enough with the chain rule and it got to be frustrating, here's maybe Gottfried Leibniz's method might be your magic bullet here. Here's what he did. He got annoyed with the complexity of this. He's like, I'm just going to call this thing U. That's easier. So therefore, he just has y equals u to the 7th. A much more pleasant looking equation. And then he wrote a note to self up here. U is the brand new name for sine of x to the 3rd plus 5x squared. So okay, let's perform his method. You want dy dx, you say? Okay, fine. What you need is a y equals equation in terms of u that has u's in it. Do we have any y equals with u's in it? Oh, why, yes, right here. How about that? Yeah. We'll take its derivative. So dy du will just be 7 u to the 6th. All right, next up, let's switch colors to green. Is there a u equals equation with x's in it? Well, yeah, sure enough, right up here. All right, we'll take its derivative. And again, this is just made or designed so that the problem breaks down a little more easily for some people. All right, u equals with x's in it. What's the derivative of this? Well, it would be cosine of that stuff. Of course, with its own chain rule of, 3x squared plus 10x. And I think you can see that we got the exact same thing that we had before. Once you reorder things, this goes here, 7 comes down. Oh, and you know what? You don't want to leave any u's in the answer, but we know what u is. It's right up here. U is just sine of x to the 3rd plus 5x squared. So really, when we're doing chain rule, whether we realize it or not, we're using Leibniz's method. Whether we formally write it out that way or not, a lot of these steps we're doing mentally, or we're doing them in a different order, and we don't realize that, we're doing exactly what he told us to do. That's why he says equivalently, or the book says, if you have f of g of x, it's just f prime of g of x. Then multiplied by the derivative of the inside, g prime. That's your chain rule part. So again, these two are the same thing. I started you guys off more this way, and now we're kind of seeing just a potato kind of thing, just a second way to do the same thing. Most people don't like it as well. They're like, I'm used to what I'm comfortable with. Other people are like, oh, thank goodness for this. I finally get it now. So I always like to have more than one approach. All right, this number 6 is almost forcing our hand into doing it Leibniz style. And since I'm supposed to teach you that concept, I will do it that way, but I will also show you a way around it. All right, the Leibniz notation looks like this. All right, the problem says find dy dx. That's what I want you to do. Okay, great. Well, that's equal to dy du. Do we happen to have a y equals equation with the letter u in it? Well, yeah, right up here. Well, what's its derivative? It's 20u. Okay, thanks. That's cool. All right. Times. Do we happen to have, hanging around somewhere, a u equals equation with the letter x in it? Well, wouldn't you know it? Yeah, we do. All right, well, what's the derivative of that? It's 5. Okay, thanks. So if this is a 3-point problem, and you guys give me 100u, I'll give you 2 out of 3 because that's fairly impressive. But I asked for dy dx. X. So I expect to have x's in my answer, not u's. But that's easy to fix. Because after all, this u right here is just a 5x plus 4. Here, now you got yourself a 3 out of 3. Now you got full credit. Because if I want dy dx, I expect x's as the variable. You're welcome to distribute. That's also 500x plus 400. It's not necessary, but equally is correct. All right, So that is the Leibniz method. That was really easy and straightforward. Now again, if you really, really, really hate this, there's nothing that makes you have to do this method. You can do the other method, which honestly is the same thing anyway, but if it makes you feel better, I'll show it to you. What you can do is just take the original problem and just rewrite it. So right here, y equals 10u squared minus 3. Yeah, I know. You probably couldn't have helped but notice I didn't write the u. Yeah, I blew it off. Because u is 5x plus 4, so I'll just dump that in instead. It's basically a direct substitution. And now I can find dy dx because I have a y equals equation with x's in it. Even though, unbeknownst to you, you're really still using what Leibniz invented. It's just a different way to think of it. Do the power rule. 2 times 10 is 20 in front. Stuff to the first, so it goes down by a power. Oh, but does the stuff inside have a chain rule? Well, yeah, it does, times an extra 5. Good, well, according to him, you have to write that. And of course, 20 times 5, you can bring that to the front. That's the 100, and the rest of it is right there. And boom, you're done. So you're going to use his method regardless of which way you do it. You can use his formula with the du dx at the end. Or if you want, you can just use a direct substitution, and you're still doing the chain rule that he invented. So no disrespect to him either way. He doesn't care. Number 7 is the final question of the section. Find y double prime, second derivative. Well, in order to find a second derivative, you have to start by finding a first derivative. The derivative of secant of 3x is secant 3x tan 3x times a chain rule 3. All right, there is a bit of a concern here, however, because of all the multiplication dots in the trig. And the concern is, you've got yourself a product rule. Oh, man. So you've got to get your u prime and v prime. U prime would be, well, the secant of 3x, the derivative is secant tangent. There's already a 3 there. There's going to be another 3, so that'll be 9. Secant 3x tan 3x. That's u prime. V prime will be secant squared of 3x times a chain rule 3. Okay. So u prime v plus uv prime is going to look like this. U prime v. You can see that the tangent got squared. It's basically just this right here, but with an extra tangent on it is the tangent squared right there. Okay, uv prime will be the two things that I circled in green. Obviously, 3 times 3 is the lead-off 9 coefficient. And then it's secant cubed because this is first power, this is squared, so that's what gives you the third power. All right, so I get that answer for the second derivative, and I feel pretty good about it. I go to the back of the book, however, and I don't see anything that remotely looks like what I just have. And I'm thinking, well, I guess I could have factored out a 9, and heck, I guess I could factor out a secant as well. Maybe that's what you're talking about. And yeah, it is. But the only problem is they can do some really nasty things on multiple choice tests by using the golden sheet of trig that hopefully you know. Oh, man. Tangent squared plus 1 is secant squared. So maybe they want to make these all secants. Maybe they don't want to have mixed trig functions. So what you could do is you could take that tangent squared of 3x out and replace it with a secant squared 3x minus 1. Remember, tangent squared plus 1 is secant squared. We're just working our way backwards. Secant squared minus 1 is back to tan squared. Now, you can combine things. Inside the parentheses, you have 2 of those secant squareds. They both have 1s on the front. So that's going to be 2 secant squared of 3x minus 1. And the thing that worries me sick is those are both great answers, the red and the green rectangle, but man, they don't look like they're the same answer. In fact, you could even rid yourself of the parentheses completely in the green just by doing distributive property and getting like an 18 secant cubed 3x minus 9 secant of 3x. That's just awful. So again, your algebra is very important, especially in multiple choice settings. So I just wanted to share that with you guys. But that gives you a pretty good, all-encompassing view of the chain rule. It's a bit of its history and some of the harder problems that you might see. So that's it. We're done with section 2.4, and I'll catch you on the flip side for section 2.5 called implicit differentiation. Until then, I hope things go well for you. I'll see you later.